Hello, my name is Josue Torres-Fonseca, and my project for this summer was on interpreting neural networks using minimal training data. So the reason I care about this problem is because we know how neural networks work mathematically, in the sense that if we had a list of words, such as from an email, we'll put those list of words into some number format, which is then input for a neural network. But it's then multiplied by a set of weights in itself, and the product of those weights are then summed up in some net input function, which might be multiplied by some bias value. In this case, now we have some output, which is then put into some activation function, which forces the output to be between some set of numbers, in this case, -1 and 1, where anything below 0 might, for example, indicate not spam, and anything above 0 indicates spam. And in this case, let's say the output should be spam. It will then use a bunch of calculus and linear algebra to fix the weights and biases so that it has the desired output. Now, that makes sense mathematically, but to an average person, it's not very interpretable to humans themselves. For all we know, it could be learning patterns such as a certain set of words indicates spam, and a certain set of words usually indicates not spam. And the reason I want to fix this problem is because state-of-the-art machine learning models today are usually very racist and misogynistic because they're trained on data on the internet, which unfortunately has racist and misogynistic ideals. We have examples such as here, where it's mostly recognized the faces of Black people being biased towards colored people, and it's raised in the human faces being biased more towards Asian people, which could be a problem if it was used for purposes such as catching a criminal using cameras. Now, MIT kind of already solved this issue using Milan, where they basically took a set of image regions and they put these set of image regions to neurons to find the top 15 image regions that cause the neuron to activate the most. Those 15 set of images would then essentially, or that set of 50 images would then essentially describe that neuron, and then they would capture those image regions where we have things something here, such as in the blue neuron, where we capture plaid and checkered patterns as a description, or in the orange neuron, where we capture the description being as a graph around animals. And it's important to have a regions here in this case, mostly because if it was just a whole image, it might just basically say animals instead of saying graph around animals, which is what the neuron specifically is meant to do. Now, this is a good model. However, the issue is that it has to use training data in the order of thousands, and it's very general data set, so it can't be used for data sets such as medical or law or any other specific group data set or domains in itself. So what I want to do is I want to create an image or the version of this model that uses a lot less training data. And the way I've done this is by using something called clip. Well, clip essentially takes an image and a set of descriptions, and it finds the best description for that image. Now, this is usually used only for one image and for the whole image in itself. I had to modify so that it can create a score based off the image regions and for the whole image if I wanted it, and so that it can create the best description for a set of image regions in itself. So after I did this, we were then able to create descriptions such as a photo of an image. Now, obviously that's wrong. This is a photo of a dog. And we think that's happening because it's having a hard time finding the pattern between the description. So it just chooses image as a default, and so it's trained on data such as this is an image of this is a photo of a blank. Now, to fix this idea, we basically use something called pointwise mutual information. Basically, what we did is we did the probability of the description, in this case image, given the image, and the probability of description is the image being used for any neuron. And essentially, if that description was used for a lot of neurons at a high penalty for how often it was used for a description for other neurons. In this case, image was used a lot for other neurons at a high penalty, and we had a better description of a photo of a dog. Now, my results here basically show how we did. We use one-word descriptions to start simple, but we're in the future use higher descriptions or longer descriptions in itself. So in this case, the human annotations are blue edges and blue and orange areas, and predicted caption is blue, which you see agrees with the image regions and the human annotations. In this other case, we have the human annotation jack-o'-lantern and the brightest part is the images, and predicted caption is fire. Doesn't necessarily agree with the human annotations, but I think it better agrees with the image region to the better description, as most of these images have fire, but not all of them have jack-o'-lanterns in itself. So there's that. Now, to give more concrete results, we are doing better than NetDissect by 0.01, which does something similar as our model, except that it had to use data in itself, and it had one-word descriptions, but so not except it did use one-word descriptions such as ours. But ours is better despite the fact that we did not use any training data and it just didn't have to use training data. Now, it's not better than Milan. We take that and we have to fix that problem. And we think one of the reasons it's not better than Milan is because of issues like this, where it seems to have a hard time recognizing abstract patterns, where this doesn't really care about what's in the image region, but where the image region is, which in this case is above images. So we need to figure out how to fix clip, or if clip can even do this one image. And if clip can do this one image, how do we fix our modified clip? If we can't do it with one image, how can we fix clip so it can do so? And basically, this is important because if we can find interpretable machine learning and find out what it's learning exactly, we can possibly find bias in a neural network and remove it. Or if we can't remove it, at least we know where the bias is and gonna have a starting place for what to do and how to fix bias in machine learning networks. Thank you for coming to my talk and have a wonderful day.